Welcome to Advanced Linear Algebra. Today, we are going to explore one of the most powerful and beautiful concepts in all of mathematics, the singular value decomposition or SVD. Whether you're interested in pure mathematics, data science, or artificial intelligence, understanding how SVD works will completely change the way you look at matrices and data.
Before we dive into the equations, let us build some intuition. Imagine you are trying to move a large, awkwardly shaped sofa through a narrow doorway. You cannot just push it straight through. First, you have to rotate the sofa to line it up. Then, you push it straight through the doorway, which is a linear stretch or translation. Finally, you rotate it again to place it exactly where you want it in the new room. In advanced mathematics, matrices act exactly like this. They move and stretch points in space. The singular value decomposition takes any complicated matrix and breaks it down into these three simple, easy to understand steps: a rotation, a straight stretch, and another rotation.
Now that we understand the concept of rotating and stretching, let us look at the mathematical formula that makes this possible. The singular value decomposition states that any matrix A can be factored into the product of three specific matrices, U, sigma, and V transpose. Let us break down what each symbol means. The matrix U is an orthogonal matrix, representing the final rotation or reflection in space. The middle matrix, sigma, is a diagonal matrix. Its diagonal entries are called singular values, and they represent the pure stretching or shrinking along the main axes. Finally, V transpose is the transpose of another orthogonal matrix, representing the very first rotation applied to the space. If you increase a singular value in sigma, the space stretches more in that specific direction. We have seen the formula, but this leads us to an important question. How do we actually find these three magical matrices? We cannot just guess the rotations and stretches by looking at a grid of numbers. Instead, we use a clever mathematical trick involving the transpose of our matrix. By multiplying our original matrix by its own transpose, we create a new, perfectly symmetrical matrix. Symmetrical matrices are wonderful to work with because they are much easier to solve and always have real eigenvalues. This multiplication step is the key that unlocks the hidden rotations and stretches inside our original complicated matrix. Building on that clever trick, let us see the exact formula that connects our matrix to its eigenvalues. When we multiply A transpose by A, the orthogonal matrices simplify beautifully, leaving us with V times sigma squared times V transpose. Conceptually, this equation is famous because it is the exact formula for finding the eigenvectors and eigenvalues of a symmetrical matrix. The matrix V contains the eigenvectors, which are the special directions that do not get knocked off their path when multiplied. The diagonal matrix sigma squared contains the eigenvalues, which tell us the exact amount of stretch along those special directions. By solving this, we find the foundational pieces needed to construct our singular value decomposition. Before we move on, let us see this with a concrete example. We will find the singular value decomposition of a simple rectangular matrix with 3 rows and 2 columns. We are given matrix A and we need to find its rotation and stretch components. Our first step is to multiply A transpose by A itself. The transpose flips the rows and columns, turning our tall matrix into a wide one. Multiplying this wide matrix by our original tall matrix gives us a neat 2 by 2 symmetrical square matrix. From here, we set up the characteristic equation by subtracting an unknown lambda from the diagonal and setting the determinant to 0. This is the standard procedure to find our hidden eigenvalues. Continuing with our calculation, we solve the characteristic equation to find our eigenvalues. Expanding the determinant gives us a quadratic equation, which reveals our 2 eigenvalues, 3 and 1. However, these are not our final stretching factors just yet.
To find the true singular values, denoted by the Greek letter sigma, we must take the square root of these eigenvalues. This gives us the square root of 3 and 1. These numbers tell us exactly how much the matrix stretches space along its two main axes. We then place these singular values onto the diagonal of our stretching matrix, sigma. Because sigma must match the dimensions of our original matrix, we add a row of zeros at the bottom. Now that we have our stretching matrix, we need to find the initial rotation matrix, V. We do this by plugging our eigenvalues back into our system of equations to find the directional eigenvectors. For the eigenvalue of 3, we get our first vector. For the eigenvalue of 1, we get our second vector. It is crucial that we normalize these vectors, meaning we divide them by their own length so that their total length is exactly 1. The fraction 1 over the square root of 2 outside the brackets ensures this. Finally, we combine these two normalized eigenvectors side by side to form the matrix V. This matrix represents the very first rotation applied to our space. We have our first rotation and our stretch. So now we must find the columns of our final rotation matrix, U. To find the first column, we multiply our original matrix A by our first V vector and then divide by the first singular value to ensure its length is exactly 1. This gives us a new vector with 3 components. We repeat this exact same process for the second column, using the second V vector and the second singular value. Because U must be a square matrix with 3 rows and 3 columns, we are missing one final column. We find this third column by finding a vector that is perfectly perpendicular to the first two and normalizing it.
We now have all the individual pieces required to write the full singular value decomposition. We place our U matrix first, followed by our sigma matrix, and finally the transpose of our V matrix. This final expression shows our original complicated matrix broken down into 3 simple steps. We have successfully factored the matrix into a rotation, a stretch, and a final rotation. Physically, this means if you apply this sequence of transformations to a set of points, it will perfectly match the distortion caused by the original matrix A. This completes our numerical example. So, we have successfully used this formula to find the decomposition. Now let us understand exactly where that eigenvalue connection comes from. We start by substituting the full singular value decomposition into the expression A transpose times A. When we take the transpose of a multiplied group of matrices, the rules of algebra dictate that their order reverses. This brings V, sigma transpose, and U transpose to the front. Notice that we now have U transpose multiplying U right in the middle of our equation. Because U is an orthogonal matrix representing a pure rotation, multiplying it by its own transpose always results in the identity matrix, which simply disappears. This leaves us with our final proven result, showing exactly why A transpose A gives us the V and sigma matrices. To truly grasp what we just proved, let us look at this geometric diagram. Here we see the singular value decomposition broken down visually. On the far left, we have our initial state, a perfect unit circle with orthogonal axes. The first arrow shows the V transpose rotation, which spins the circle but keeps its shape. The middle arrow shows the sigma matrix in action. Notice how it stretches the circle into an ellipse. The amount of stretch along each axis corresponds exactly to our singular values, sigma 1 and sigma 2. Finally, the last arrow shows the U matrix, applying a final rotation to the ellipse, placing it in its final orientation. This diagram perfectly illustrates how any matrix transformation is just a sequence of rotate, stretch, and rotate. Now that we have a strong geometric understanding, let us look at a real-world application. How can we use the singular value decomposition to compress data, such as a digital photograph? The core idea is to create a smaller, simpler version of the matrix that still captures the most important information. We do this by keeping only the largest singular values and completely ignoring the smaller ones. The largest singular values represent the most significant patterns in the data. By throwing away the smaller values, which often just represent noise or minor details, we save massive amounts of memory and computational power. This technique is the absolute foundation of modern digital media compression. This brings us to the mathematical formula for compression, known as a rank 1 approximation. Instead of rebuilding the matrix with all its pieces, we rebuild it using only the single largest singular value. In this formula, A is approximately equal to sigma 1 times U1 times V1 transpose. Sigma 1 is the largest singular value, representing the dominant stretch. The vector U1 is its corresponding column from the U matrix, and V1 transpose is the corresponding row from the V matrix. If we were to include sigma 2, the approximation would get closer to the original, but it would take more memory. This formula shows how we intentionally lose minor details to achieve a highly efficient compressed matrix. Let us apply this compression formula to the exact same matrix from our previous example. We want to find a rank 1 approximation. We start by substituting the exact numerical values we found earlier. Notice that we have completely dropped the second singular value, which was the number 1, along with its corresponding vectors. We are now working with only a fraction of the original data. To simplify the expression, we first multiply the constants together outside the matrices. Multiplying the square root of 3 by the normalization fractions gives us a simple constant of 1/2. This sets us up for the final matrix multiplication. Continuing with our compression, we now multiply the tall column vector by the wide row vector. Multiplying a column by a row in this specific order always generates a full grid of numbers. We distribute the values and then multiply everything by our constant of 1/2. This gives us our final compressed version of the original data. If you compare this new matrix to our starting matrix, it is not exactly identical, but the numbers are remarkably close. Physically, this means we successfully compressed the data while keeping the main pattern intact. In a real photograph with millions of pixels, this process reduces the file size drastically without visibly changing the picture to the human eye. We have covered a lot of ground today, so let us review the key takeaways. First, the singular value decomposition shatters any complex matrix into 3 fundamental actions: a rotation, a stretch, and a final rotation. Second, the stretching factors, known as singular values, tell us exactly how much importance or energy is contained in different directions. Finally, by keeping only the largest singular values, we can compress massive amounts of data into tiny packages while keeping the most critical information intact. You now understand the ultimate tool for simplifying complex mathematical transformations. Great job following along, and keep practicing these concepts.